Hello, everyone. I hope everyone is having a good night. And let's go continue our talks. So to start off with, let's remind ourselves about electronegativity, which is the ability to attract electrons in a chemical bond. And we kind of talked about it before, but I think it's more important to really talk about it now, simply because now we know what a chemical bond is. And if we would look at, let's say, NaCl, we know that Na is going to donate its one valence electron, and Cl is going to accept that one valence electron, right? And we can see here that clearly, because Cl has that one other extra electron within its vicinity, that all of that negative charge from the electrons is going to be greater than the positive charge that comes out of the nucleus. So we could say that this whole ion is going to be very negative, whereas this Na, because that positive field coming out of the nucleus is stronger than all the electrons can put out, this sodium ion is overall positive. And really, when we talk about positive or negative, it's like we're an outside looker looking in to the sodium. So if someone were here, here's a person. Apparently they're laying down. That's a not good person, but they are looking at that and they're looking at that. And if they were looking at both of those, they would see that the sodium is positive, the chlorine is negative, right? And what we can say is that within, we know that there's an attraction here within this bond. We can call this whole thing, this ionic compound, this is an example of something that is polar, where there is a clear division of charges. Super obvious. Here's all of the negative. Here is all of the positive. Let's take a look at a covalent compound, okay? For example, let's look at one of our Hofbrinkels, chlorine. Cl. And we got our other Cl. Let's make them closer. They can get nice and close. Here's our other Cl. So they're not bonded right now because they haven't really shared. And we can see that because they both have the same amount of electronegativity, we can actually draw these two electrons right in the middle. They're flat in the middle. So the two shared electrons are equidistant from both nuclei, both chlorine nuclei. And that's because the electronegativity difference is the same. There is no electronegativity difference. So the electrons are being pulled evenly. And thus, right in the middle. And that's really, when we talk about this idea of electronegativity, that's really what we're talking about. Who's pulling those electrons? Up here, chlorine had such a strong pull that it pulled all the electrons into itself. Over here, neither of them have a stronger pull, so neither of them can win. Right? Now, let's look at a different situation, a third situation. Let's look at H and Cl. H and Cl. We know that H has 1 valence electron and chlorine has 7 valence electrons. So we can tell that chlorine is going to give off 1 or share 1 with hydrogen is going to share 1. In other words, they both make 1 bond, right? However, if we look up the electronegativity values, and I think I have that, no, that's in my reference table, I can tell you that chlorine is much, much higher. I can actually look that up. I have the reference table here. That is the AP reference table. We want the Regents reference table. Here we go. So hydrogen, number 1, has an electronegativity of 2.2. Let's write that down. 2.2, whereas chlorine, which is number 17, chlorine has an electronegativity value of, and I hope you can see that chlorine's electronegativity value is, where is it? 3.2. 3.2. So clearly chlorine has a much higher electronegativity value. So if I were to draw out those shared electrons, I'm probably going to draw them closer to the Cl. Now, notice how I'm not drawing brackets like I did with this Cl and NaCl, because it's not that Cl pulled the electrons completely away from hydrogen here. It's just they're much closer to chlorine. So what we can say is that the electrons in H and Cl are being shared, but not shared evenly. Right? Because Cl's electronegativity value is so much higher, the electrons are going to exist closer to Cl than H. Okay, now we have to note that this is not as strong a negative charge as the chloride ion. As strong a negative charge as in NaCl. This one right here, not nearly as strong as this over here. So we're going to give it what is called a partial charge, which is simply a weaker charge. Makes sense, right? And we have our 2 partial charge signs for a partial positive charge. We're going to draw, so it's kind of that swoopy D-looking shape. It's actually, I believe, a lowercase delta. And then the plus is for the positive, so that shows it's a positive. And then for the partial negative charge, because we obviously have both, swoopy with a negative sign. Okay, so excuse me, those swoopies are supposed to be the same thing. So let's look to see how we're going to draw that on a molecule like HCl. HCl. And we'd simply draw positive, negative, right? Let's look at some other examples here. Let us do NH3. H, 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 2 dots. We can look up the electronegativity values. H will have a lower electronegativity value, so positive, 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 sorry, and negative, right? Let's look at our friend water. O, H, H, and positive, positive, negative. And the last one, let's look at our friend fluorine. And the reason I had us draw out fluorine is that there are kind of two different types of bonds going on here. Here's too much. Here is one type of bond, and we're going to call that type of bond. This is a non-polar covalent bond, whereas most of these bonds up here, that one, this one, this one, that one, that one, these are all examples of polar covalent bond. It's really easy. If there's an electronegativity difference of 0, when difference in electronegativity equals 0, it is non-polar. When difference, I should say nonpolar covalent bond of electronegativity is greater than 0, then it's a polar bond. And the reason I am not writing polar covalent bond is because it could be either a polar covalent bond or an ionic bond. An ionic bond is a polar bond. Now, biggest difference, and I know I talked about this before, but I like pictures. The biggest difference between an ionic and a polar covalent, if we look at pictures, we can see here, this is our NaCl friend once again, and we can clearly see this divide right here, where there's the Cl and where there's the Na. Right? Those are two very different things. If we were to look at HCl, once again, we have kind of this blended area where there is definitely polar in that we have all of this negative over here. We have this positive over here. But it's definitely, you can see the sides, negative, positive, right? But it's still not split. It's not two circles. It's one big blob. Whereas for a regular old non-polar covalent bond, we can see that this charge, it's kind of split evenly throughout. Okay? So polar and non-polar bonds. Yeah. So please don't confuse the idea of a polar covalent bond with an ionic bond. Remember that ionic bonds are also polar. Okay? I hope everyone has a good night. Bye.